All right, so in this video, I'm going to show you two exercises from the end of the chapter problems. The first one is exercise 9.1, where we want to use linear programming to solve for this problem. We have to produce 1 pound of an alloy that has at least 30% lead and 30% zinc. Okay, and we want to mix lead, zinc, and I think tin. Okay. All right. So if this table is given, where we know the percentage of the lead, zinc, and tin, and also the cost per pound for each alloy, right? So this is alloy number 1, alloy number 2, alloy number 4. We want to find how much of alloy 1, 2, and 3, and 4 we should have, basically, to satisfy these two constraints, where we have 30% lead minimum and 30% zinc, by minimizing the cost. Okay, so we're going to see how much we have to produce alloy 1, 2, 3, and 4, such that we satisfy these two constraints at the same time lower the cost. So we're going to create a spreadsheet like this, where x1 through x4 are the pounds of alloy 1 through alloy 4. Then we're going to have left-hand side of the first constraint. The first constraint says the amount of lead should be less than 30%, should be minimum 30%. So, so the way we do this is we say 20% of x1, 10% of x2, 40% of x3, 50% of x4. This sum should be less than 30. I'm saying it should be greater than 30 because the minimum is 30%. So it should be more than 30%, right? And the second constraint is if 20% of x1, 40% of x2, 50% of x3, and 30% of x4, they should be greater than 30 again, because that's the second constraint. And what we are optimizing is x1 times $6 per pound, x2 times 6.3, x3 times 7.5, and x4 times 8, and that's what we have here. So that's the constraint. And these are the two constraints. As an objective function, we're going to minimize the total cost. So then what we're going to do is we're going to go to the solver, and then we're going to solve. We're going to minimize the objective function, which is this cell, subject to two constraints. So here, left-hand side, this time should be bigger than or equal to the right-hand side. So A4 should be bigger than or equal to B4, and A5 should be bigger than or equal to B5. Okay, because we have to create at least 30% of those elements, like lead and zinc. Okay, and the variables are going to change or modify or optimize are x1 through x4. So here are the variables. All of them are non-negative because this is a concentration, or the not the concentration, basically they're the mass of the elements or the alloys, right? The mass of the alloys, so those should be positive. Okay, and we're going to do simplex programming options. I think you can say maybe 100 seconds just to make sure nothing goes beyond the hand, or everything is in control. Okay, now we're going to go ahead and solve it. Actually, let me cancel this. Let me initialize everything by just 1, 1, 1, 1. I'm going to go to solver and solve it. There you go. So that's the solution. Okay, so hopefully this is useful. Next problem we're going to look at, let me save this, is 9.4. Okay, so let's move on to 9.4. All right, in exercise 9.4, which is basically a nonlinear set of equations, we're going to look at three reactions. So A plus B goes to C plus D, B plus C goes to E plus F, and A plus E goes to G. We have the reaction rate constants, K1 through K3. In terms of the concentrations, we can just, this is the chemical formula for every reaction. It's just product divided by reactant, the concentration product divided by the concentration reactants. We have the numerical value of the Ks, right? We define extent of the reaction. Well, based on the extent of reaction, you can write the concentration of every species here, Ca through Cd, in terms of x1, x2, and x3. So these are the reaction or extent of reactions where we have to solve for. So x1 through x3 are basically the unknowns. And basically using these three, we can relate all the concentration A, B, C, D, E, F, and G to the initial concentrations of other species. Okay, so we have like 7 equations right here in terms of x1 through x3 only. 3 unknowns, x1 through x3, 7 equations. Okay, we also have the relation between concentrations and rate constants. For every reaction, we can write this, and this is basically just reordering these 3. So you can cross-multiply K1 by CACB, move it to one side, and then subtract from CD, CCCD, you get this equation. And the other two basically are reordering version of these two. So nothing new, right? Okay, so what we're going to do is we're going to plug in the CA through CG, all of them, into here. So at the end of the day, we're going to get equations in terms of x1 through x3 and CA naught through CG naught. Okay, so there's no more CA through CG. Everything should be either x1 through x3 or CA naught to CG naught. And I'm going to solve for x1 through x3 using the solver. So here's the setup. We have the initial concentration Ca naught to Cg naught. We can make a guess. Let me see. I'm sorry. I think the initial concentration are given, so these are not guess, right? So Ca naught, Cb naught 1, all others 0. So we have 1, 1 here, 0 everywhere else. X1 through x3, we make a guess right here. So I'm gonna guess 1, 1, 1, and make sure the extent of reaction should be between 0 and 1. So if the solution comes out to be bigger than 1, that's invalid. It has to be between 0 and 1. Okay, and I know the rate constant, K1 through K3, they're just 1, 2, and 4. I have them here. Then here, I just write the equations for Ca through Cg. So you see these equations right here. I have the equivalent version right here. Let me just go over the first one. The first one says the blue cell, right? Oops, not that. Okay, so one more time. It's Ca naught, so right here, minus x1, which is the green cell. So green cell times purple, so it's x1 times Cb naught, which is true, minus maybe the brown cell, B10, which is x3 right here, and then times the blue cell, which is Ca naught, and that's right here. So the equation, the first one, the right-hand side of the first one is right here. So I'm just writing the right-hand side of all of these, right? Okay. Okay, so this is the right-hand side of all equations. Residual, well, so the right-hand side should be exactly equal to the left-hand side. Okay, so I have the Ca, well, okay, so these ones are basically what I calculated so far is Ca to Cg. Then the residual actually comes here. We have 3 equations here. The residual would be this minus 0, which means just this. The second residual is this minus that, which is again the left-hand side, and here's the left-hand side. So these residual that I have is nothing but the left-hand side of these equations, which is a concentration of C times D. So here's C times D, right? And then minus K1, which is the purple or the brown or the pink cell, and then times CACB, which is the brown, and times the green. So this residual is nothing but the left-hand side of this one, the second residual is the left-hand side of the second equation, and third residual is the left-hand side of the third equation. CACB all the way to CG are given right here. I calculated already in terms of x1 through x3. So at the end of the day, I need to minimize the residual on all of these. Okay, so 2 ways to do. Either you can square them and then get the sum of squared and minimize the sum of squared, or you can just individually minimize them. So let's see how I did it here. Close. So we go to solver. Okay, so let me just cancel this. Okay, so we also create the residual squared, which is basically you get this cell raised to the second power, you drag it down, and oh, I have to make the initial guess one more time. Okay, and then we get the sum of the residual squared, which is sum of these three cells. Okay, so then I think everything is ready. We're gonna go to the solver, and so we're gonna minimize the sum of squared of the errors by changing the variables, which is x1 through x3, these three. And this is a minimization problem. All variables are non-negative, so those are extent of reaction, x1 through x3. Remember that should be between 0 and 1 according to the problem right here. And we're going to make the timing to 100 seconds. I think this is good. We're going to go ahead and solve it. And the result we get are these. So the solution found, we're going to keep the solution, and this is the result. This is the extent of reaction, all of them between 0 and 1. And so you see a problem here because now we see the concentrations of A through G, some of them are negative. So this is not acceptable. One thing we forgot was that the concentrations actually need to be positive, not really, well, x1 through x3, the extent of reaction, of course, need to be positive. Ca to Cg, which are the concentrations, also need to be positive. So we're going to go back to solver and add this constraint that all these 7 constraints, Ca through Cg, all of them need to be positive. And with that, I think we can go ahead and solve it. And after you solve this, you see the solution is going to be that. So let me just do it one more time. So it's going to be 111 initial guess. But with this initial guess, we get actually negative concentrations, but I think that should be fine. Solver can correct that, and we can go ahead and solve it. You see that now the concentrations are positive, right? And these are also between 0 and 1, and the error is almost 0. So we found a solution using the optimizer or the solver in spreadsheet. Hopefully this is useful. All right, so thanks so much for watching. Stay tuned for the next video on VBA programming and spreadsheet calculation for regression.